your kind introduction, and thank you for having me on this short notice. I have to excuse Christian, who you might have experienced or expected here. He unfortunately got sick, and now you have to deal with me instead. Nevertheless, I'm going to talk about the same topic. And first of all, I'm coming from Oldenburg, where our group is located now, which is in the northern part of Germany. And as you can see, we have the northern coast really close and some nice campus within nature. So if you're motivated to come and visit and discuss science or discuss collaborations with us, you're more than welcome, but don't be fooled. Bring your rain gear. It's mostly rainy up in the north. Let me just shortly introduce the group's philosophy, the group's concept to you. So we are mostly doing cavity spectroscopy, and there we are introducing or investigating several platforms that are of interest to us. And one is nonlinear bosons in synthetic lattices, where we investigate several material classes like perovskites, organic materials, semiconductors, and especially TMDCs, which is also my topic. And then we have quantum materials for photonics, where it's going more about the inherent material properties, where I'm going to talk about during this talk, especially with the collaboration with Alex Högle and Johannes Scherzer, who are also here in the audience, where we just showed correlated magnetism in a MOE lattice. And the last part and the pillar of our group is fundamentals and applications of light-matter coupling in cavities, where we're mostly investigating single photon sources and use the Purcell enhancement of cavities to extract a higher yield. But within this talk, I want to have a talk about exciton-polaritons and why we are using microcavity exciton-polaritons for our research. And I will do this only shortly because I checked the program and there was already a quite heavy polariton session. So just as a reminder, we have two distributed Bragg reflectors that build up our optical cavity, and in between those mirrors we put our exciton hosting material, in my case mostly TMD monolayers or heterobilayers. And now if we meet proper conditions, we actually get them to strongly couple, and we have this strong light-matter interaction, which is distinct by this avoided crossing of the pristine modes, where you have the cavity and the excitonic mode, and here's the detuning of the pristine excitonic mode versus the cavity mode, and then you have the Rabi splitting and the oscillation between light and matter part between those systems. And why do we use the exciton-polaritons? Because especially of this intrinsic property of the polaritons, that you have the photonic part, which is optically accessible and can be confined in pattern cavities, as well as the excitonic part, where you have large interactions and a magnetic response. Our system approach is the open cavity, and we went from monolithic crystals to the open cavity mostly because we went to a new lab, had to establish everything, lost a big cleanroom facility, and this is a reasonably cheap approach to get high quality cavities. And now we are not only using it because it's cheap, but we also want to harness its intrinsic properties, which is the versatility. So we have the two individual DBR mirrors mounted on piezo stacks, which is for the top mirror an XYZ, for the bottom one XYZ, plus additional goniometer and rotational freedom. And with this, we have total control over the energy of our cavity systems, as well as of the position and the relative tilt between those two mirrors with the optical active material. And one part where we use this at room temperature in this configuration is where we implement photonic lattices and show that we have tunable polaritons over a large range. And just recently, we also implemented a tip tilt approach in a 1D lattice, which has a defect mode, and it emulates the SSH Hamiltonian, which is the most trivial topological Hamiltonian. And there we have actually direct access to its topological invariant, which is the Z phase. So if you're interested, this will be soon on archive. And now talking more about TMDs, we went to AutoCube and said, hey, we want to have an open cavity at cryogenic temperatures with magnetic field control and optically accessible. And together with them, we designed an approach where we have this cage structure, where we have one of the DBR mirrors mounted on an individual stack, and the second DBR mirror fixed to a titanium platform. And this platform can be moved in XY relatively to the micro objective. And one of those mirrors has a mesa-like shape, so we have a reasonably close approach that we can go to small cavity length and go to small fundamental modes of our cavity system. And in this mesa, we implement photonic trap potentials to further harness those properties. So let's combine. We have the cryogenic temperature. We want to have, sorry, let me check if it runs. Yeah, so by tuning the distance between the two mirrors, you can actually see that you can tune your cavity resonance through, and this is perfectly repeatable, so we have perfectly control of the cavity resonance. Then I told you that we implement hemispherical cap indentations, which is a photonic trap potential, and this gives us like a Gaussian mode, like a mode development. And within this cavity, with 2 DBR mirrors, we have Q factors of roughly 600, which is sufficient for our strong coupling regime, which you can see here, where we have put a molybdenum diselenide monolayer on top of the bottom DBR, and then you can see that you have the SP, the D mode is not really visible, and then there's of the next longitudinal mode, the S mode, and here you can see the avoided crossing of the exciton line and the cavity line, which is tuned through by applying a DC voltage. And this yields a Rabi splitting of 16 MeV with this monolayer, and this is for extremely long cavities. In this case, if you do the estimations, we have roughly a 5 micron separation between the two mirrors. And by going closer and closer, you further enhance the strong coupling and the Rabi splitting. So the next part we wanted to investigate is how can we charge tune our devices. And there we are lacking all the experience and expertise, but luckily Alex was so kind to support us with samples and give us the opportunity to study those within our systems. And here we have a basic MOSA2 monolayer covered by a back gate and a contact gate. And if we apply a gate voltage to those, you can actually see that in the neutral point you have the exciton, and applying a gate voltage you have the repulsive and attractive polaron branches. So all in all, within our cryo cavity system, we have the spectral tunability, we have photonic potentials implemented of various shape and design. We have shown that we have strong coupling with monolayers, and we have shown that we can have charge tunable monolayers within this cryostat. So the next natural step was to go for more sophisticated samples. And there, Johannes Scherzer came to us. He fabricated a sample where he did the pre-characterization. And we have a molybdenum diselenide, tungsten disulfide heterobilayer. And this is covered in a fully gated structure. And what they did first was to estimate, okay, what type of band alignment do we have, and what is the type of stacking that we have. And there they did already a great deal of research. And here, by applying a gate voltage to the top and bottom gate, you can actually see that the M1 and M2, which are the Moe-confined exciton peaks, are perfectly dispersionless, and this suggests type 1 band alignment and an intra-layer exciton. So the next step was, okay, let's charge this monolayer. And first of all, we have to look at our design. So the M1 peak is located at the center of a Moe unit cell, and the M2 at the edge or in between. And if we now apply the gate voltage and load electrons step by step into our Moe crystal lattice, you end up by charging, and you have 4 distinct peaks, the M1, M2, M1 minus, and M2 minus. And for us, interesting is the M1, which is the neutral Moe-confined exciton peak, and the M2 minus, which is a polaron-like peak. And with this, we have shown that we have a charge-tunable device. We can control the filling factor, and that we have Moe-confined excitonic states. So what we did next, we loaded all of this into our cavity. Johannes came with the sample, and we did the study together. And what you can see here is for the ungated device, the M1 neutral exciton transition, and you have the avoided crossing with the cavity mode and the Rabi splitting of 9 MeV. And in the bottom panel, you can actually see the gated device with a filling factor of 1, roughly, and as well, you have the avoided crossing and the Rabi splitting of 6.2 millielectron volt. And here, what is interesting is that you have a transfer of the oscillator strength from the M1 peak to the M2 minus. Right? You can see, starting with the ungated sample, no electrons per lattice side, you have the maximum of the Rabi splitting, and it linearly decreases, and then at a given point, you charge it, the lattice that much, you fill it up, and you reach the maximum of the Rabi splitting at a filling factor of 1. So next, we made use of the possibility to apply a magnetic field within our cryostat, and here you can see the white light reflectivity data for several magnetic fields in right and left circular polarized detection. And what you can see here is the detuning at a given point where there's the B field, and you can see that you have actually a big Siemens splitting, and the important part is that it's already present for very low magnetic fields. And if you extract now the effective G factor, you can see that it's really humongous, that for the upper polariton, you have G factors reaching below -30, and for the lower polariton, you have G factors like -25. And if we compare this to the M1 state, which is the neutral exciton Moe confined state, you can see that the G factors are actually quite low and symmetric, and this is represented also if you extract the exciton G factor, that the M1 peak is perfectly well aligned with the MOSA2 monolayer-like feature with a G factor of roughly -4, and within the M2 minus peak, you have for small magnetic fields humongous G factors of -31. And this is clearly a hint that we have within our sample correlated magnetism, which is present in the small magnetic field range, and afterwards it's going again to the monolayer-like behavior. So let me summarize what we did. So we have shown that we have in our cryo-open cavity the strong coupling possibility with TMDC monolayers, heterobilayers. Just recently we have also shown strong coupling with molybdenite, mono and bilayers. This will also be published soon, hopefully. And then that we have, with the help of our collaborators, charge-tunable devices and charge-tunable Moe confined states. And within the magneto-optical response, we have like this drastic, humongous G factor, which is present for the M2 minus polaron like feature. And as said, this is a clear hint for us that we have a correlated magnetic phase on this triangular spin lattice. With this, I'd like to thank you all again, especially for being here in such a big audience, and thank you for having me.
Great talk. We have plenty of time for questions. Maybe I can start with one?
Yeah, sure.
So in your cavity, so you quoted arbitrary units there. So what is actually the tuning range of this cavity, and in terms of the distance and energy? Is it possible to do it further into visible or IR range?
The tuning range is dependent on the stepper, right? You have a maximum voltage you can apply, and there we have a maximum tuning range of 1 micron. And this tuning range transfers then into different energy scales, depending on how far or close you are. Mm-hmm. But it ranges from several hundreds of millielectron volts to electron volts if you're super far away.
So the cavity is in the order of like microns apart?
The cavity here is, I believe, the 4th fundamental mode. So you are at 1 micron or something.
Right. Thank you.
So pretty close, actually.
Thank you. Any other questions? Yes.
Yeah, thank you for the nice talk. I was wondering about the room temperature setup that you showed. That included a rotator and also goniometers, whereas the low temperature setup, it did not have those degrees of freedom. Would that help you, or how, do you compensate that somehow? I assume the gonios are to planarize the
gonio
cavity, right?
would be a massive help, for sure, because here we have to use our mesa structure to get reasonably close, and we just experienced within some experiments that it actually helps if you break away some parts, that you have a smaller footprint to get closer, because you can't actively tune the tilt between the two mirrors on the micrometer scale or nanometer scale. There you would need to implement additional piezos. But it also gives a bit of instability. So for the cryo application, we skipped it mainly because of the issue of space, right? You only have the tiny stick, and there to fit an additional goniometer was just not possible. But also in regards of stability, it's more stable if you have less steppers that vibrate against each other.
Okay, thank you, yes.
Welcome.
Great.
Thank you for this nice presentation. I have a question about this Q factor that you quoted.
Yeah.
What is limiting this? Is it vibrations or is it the coating?
We outrule vibrations, and here we measured with a dBr pair of 7 and 5 dBr pairs, and there you end up with a Q factor between 600 and 1000. And what we experience, especially in the room temperature cavity, if you are in contact with the two mirrors, the quality factor gets better because they then oscillate within synchron. But at cold temperatures, we didn't see this, and so it's limited by the mirrors.
Okay,